Back in this lesson, we're going to learn about probability distributions. A probability distribution shows us all the possible values of a random variable and the probability of each value occurring. Probability distributions are similar to graphs and tables that we've worked with before. The difference is that instead of simply displaying data, a probability distribution shows how probability is distributed across all possible outcomes. And we can represent a probability distribution using just a table or a graph, which makes it easier to see which outcomes are more or less likely. We're going to start by learning how to construct and interpret probability distributions. Then we'll look at the difference between theoretical probability distributions, which are based on what we would expect to happen mathematically, and then empirical probability distributions, which are based on what actually happened in collected data. So we're going to start with some notes on graphing probability distributions. Every probability has to be between 0 and 1. And this should probably be review on probability. Everything has to be between 0 and 100%. 100% probability means something definitely will happen. A 0% probability where 0 means it definitely will not happen. And all the probabilities have to add up to 1. So when we have multiple probabilities, they all have to add up to 1 or 100%. So let's take a look at our first example. It says, which of these graphs does not show a valid probability distribution? And we have A, B, and C to look at here. Our random variable x, we have when x is 0, 1, 2, 3, or 4, and we're given the probabilities for each x value. And the key takeaway from these questions is that all the probabilities have to equal 1.0. So here 0 is for A, 0 is 0.2, 1 is just 0, and I'm just adding the probabilities. For 2 is 0.3, and this is for A. For 0, 1, 2, for 3 is 0.2, and for 4 is 0.3. And then we're going to add all these together and see if it's 1.0, and it is. Let's check B. For 0, the probability is 0.3. For 1, the probability is 0.1. For 2, it's 0.2. For 3, it's 0.1. And for 4, it's 0.4. If we add all of those together, we get 1.1 or 110%. And that's not possible. So that's an inaccurate probability distribution. It's an invalid probability distribution. And we're going to assume C is 1.0. You can double check that if you'd like, but B is the correct answer for this one. Okay, let's look at another one. We have a graph and we have a table as well. And here we're just matching the table data to the graphical data. It says which graph correctly displays the probability distribution. So we've got a table and a graph here, and we just want to make sure that they match up. So when x is 0, our probability is 0.314. If we look at for A, it looks like it's about 0.25 or 0.26. So that automatically we can cross out A. For B, it looks like 0 is at about 0.314. So let's go to 1. 0.384 is the probability that x equals 1. So we'll go to 1 on our graph and see if that makes sense. 0.384, it's just about almost to 0.4 there. When x is equal to 2, the probability of that is 0.213, and that looks about correct there as well. If we check C, it looks like right away when we look at a probability of x equaling 0, 0.314, this looks like it's almost to 0.4, so we can cross that one out. So again, we're just matching the table data to the graphical data. Let's do one more of these here. This one's a little bit different. It says Mitha and her roommates made a spinner to help them assign daily chores. Every day they each spin the wheel and they do the chore that the spinner lands on. The spinner is set up like the one below. with 6 equally sized spaces. Half the spaces correspond to bathroom chores, and there are 2 spaces corresponding to kitchen chores and 1 space for a living area chore, or I guess we can think of it as a living room. So 3 bathroom spaces, 2 kitchen spaces, and 1 living room space. And it says which graph correctly displays the probability distribution for someone's assigned chore on a given day. Okay, so we have 6 total spaces. That means 6 is going to go on our denominator for the total for each of these probabilities. So if we want to decide the probability that it's bathroom is 3/6, and that's equal to 1/2. The probability that it is the kitchen, 2/6, or 1/3, and the probability that it's the living area is 1/6 of a probability, and that's just simplified to 1/6. Now we can just divide 1/2 is 1 divided by 2, or 0.5. 1/3 is 1 divided by 3.33 repeating. And 1/6 is 0.166 repeating. And so now we have our decimal values for our probabilities. So for B on our graph, it should be 0.5. And it looks like all 3 answer choices show us 0.5 for B. So moving on to K for the kitchen, 0.33 repeating is what we get for the kitchen. So that's looks like A and B are close to 0.2. So that can't be right. So we're going to cross out A and B. And that just leaves us with C at 0.3 repeating. And if we want to check, L is 0.16 repeating probability. And it looks like it's about 0.166 repeating for the living area. All right, next is probability with discrete random variables. And a discrete random variable is a variable that represents a specific countable set of possible numerical outcomes. So each possible value of the random variable has a probability associated with it in the probability distribution. To find the probability of an event involving a discrete random variable, we identify which values satisfy the event and add their probabilities together. For example, phrases like no more than 1 means that we include every possible value up to and including 1. So again, the main idea here, we're identifying the values that fit the event, and then we're adding those probabilities together. So here we have some table data, and we're not necessarily going to be adding all of these probabilities, probably just some of them. It says Cora is playing a game that involves flipping 3 coins at once. Let the random variable h be the number of coins that land showing heads. Here's the probability distribution for h. And we have number of heads, 0, 1, 2, and 3, and then the probability for 0 heads, 1 head, 2 heads, and 3 heads. And it says, what's the probability that Cora flips no more than 1 head? Okay, so no more than 1 head. We have to define what that is. Probability of no more than 1 head. Well, that means that it's got to be less than 1 head, but it could also include 1 head from the coin flip. So we're going to add the probability of 0. I'm going to write it like this, actually, where h equals 0 plus the probability of h equaling 1. And we have these probabilities in our table. So this is 0.125 plus 0.375. And when we add those together, we get 0.5. And that's the probability of no more than 1 head, or 0 heads and the probability of 1 head. That's another way to say that. Okay, on to our next example. Here it says a furniture factory makes a 4-piece desk. Quality control at the factory has randomly supplied numerous desk sets and determined the number of damaged pieces in each set. The table below is a partially completed probability distribution for the random variable x, where X represents the number of damaged pieces in a randomly selected desk set from this factory. So we have a probability distribution, but it looks like they've left out where X equals 4, the probability for where X equals 4. And it says, what's the probability that a randomly selected desk set contains exactly 4 damaged pieces? So here we're going to use the total probability rule, and that just states that all the probabilities have to equal 100% or 1. So we're going to add all of our probabilities. So the probability that X is 0 plus the probability that X is 1 plus the probability that X is 2 plus the probability that X is 3 plus the probability that X is 4. Those all have to equal 100%. So that's all has to be 1.0. And so now we're just going to write what these values are. So 0.75 plus 0.14 plus 0.07 plus 0.03 plus the probability of X equals 4 is equal to 1.0. And if we add these probabilities all on the left side, we get 0.99 or 99% plus the probability that X equals 4 is equal to 1.0 or 100%. And then this is just simple algebra. We're going to subtract 0.99 on both sides. And we get that the probability that X equals 4 is equal to 0.01 or 1%. So again, we're just using the total probability rule. In probability distributions, this is also referred to as the sum to 1 rule. That would be more exact for this probability problem with probability distributions. Okay, we're going to do one last example with this same topic here. Cora is playing a game that involves 3 coins. This time we have a slightly different question. It says we've got heads and tails, and we want to find the probability that heads is less than 3. So this is not less than or equal to 3. It's just less than 3. So we're going to include all of this data here that's less than 3. And we're just going to add all of those numbers together to find our probability that the heads is less than 3. And if we check that on our calculator, we get 0.875. Okay. So if it were less than or equal to 3, we would include all of this data and it would be 100%. But this is just less than 3. All right, next we're going to look at theoretical probabilities. And we're going to learn how to create a theoretical probability distribution for a discrete random variable. And remember that a random variable like X, it assigns a numerical value to the outcomes of a probability experiment. But sometimes more than one outcome can produce the same value of X. For instance, if we have 2 permutations, remember permutations is where order matters. If we have 2 permutations of A and B and A, both of those could mean X equals 1. I'm just going to write this. So both of those could be Px equals 1, and this could also be Px equals 1. So there's 2, you can think of it as 2 combinations, but technically it's a permutation because the order matters. And when we have those 2 different types of combinations, we would add those probabilities because the probability that X equals 1 happens twice. So when we see things like that, we're going to add them together. And our goal is to create a table that lists every possible value of X along with its probability. And as always, for the probability distribution, each probability has to be between 0 and 1, and all the probabilities have to add up to 100%. Okay, so let's take a look at our example problem here. Kayla is designing a video game. When a player defeats an enemy, there's a 30% chance that the enemy drops an object for the player to claim. and there's a 70% chance that they drop nothing. Suppose a player defeats two of these enemies, and then we categorize them as dropping the object or not. And here's a sample space showing the possible outcomes, or in another way, showing the combinations of what could occur. So when they defeat the first enemy, and when they defeat the second enemy. And so when they defeat the first enemy, actually, let's take a look at our answer choices here. It says, let X represent the number of objects dropped by the pair of enemies. Which table represents the theoretical probability distribution of X? Okay, so let's think about what's happening here on this table. We have X is 0, X is 1, and X is 2. And X is the number of objects that's dropped by the two different enemies that are defeated. So if X equals 0, then nothing dropped. If X equals 1, then one object was dropped by an enemy defeated. And if X equals 2, then two objects were dropped by an enemy that was defeated. Okay, so now let's use the table to define what's going on here. First enemy, it says N means not or nothing was dropped. D means that an object was dropped. So our first column, or excuse me, our first row here is the probability, or actually I'll just say this is just X is equal to 0. Nothing was dropped. For the second one, nothing was dropped on the first enemy, something was dropped on the second enemy. That means we got one item that was dropped. For the third column, something was dropped from the first enemy, nothing was dropped from the second enemy. Here we also have X equals 1 item dropped. And for the last column, we have X equals 2, where an item was dropped from the first enemy and an item was dropped from the second enemy. Okay. So we have probabilities now for each of these. So if we look at our first row, the probability of nothing dropping is 70%. So the first enemy and the second enemy, if we want to find the probability that X equals 0, that's equal to 0.7 times 0.7. This is an and probability statement. And so we're multiplying. And we get 0.49 that the probability is X equals 0. Now for the second part, the probability that X equals 1, there's two instances of this happening. But we're going to write the first instance of the probability where X equals 1. And nothing dropped. There's a 70% chance nothing dropped times something did drop is a 30% chance. So that's 0.21 or a 21% chance. Now let's do the same thing for this third row. Again, this is probability that X equals 1. And we're saying that something dropped, that's 30% chance times nothing dropped is a 70% chance. We're going to multiply those together. We also get 0.21. And the probability that X equals 2 is something dropped is a 30% chance something dropped. And then something dropped again from the second enemy is another 30% chance that that would happen. And that's 0.09 or 9% chance. Okay, so when we're looking at our table, here's our first column. I'm just going to put, well, I guess we'll circle it. Here's our first column in our table. The probability that X equals 0 is 0.49. And we can see that in all three of these answer choices. So we're good to go there. That's accurate. But when x equals 1, we have two instances of x equals 1, or two combinations where x equals 1. And we're going to add those probabilities together. And so now this is 0.21 plus 0.21, which gives us 0.42. And so that's the probability that x equals 1. That's the true probability that x equals 1. These were just individual instances of it, and we've added them together now to find the actual probability, which is 0.42. And we can see that in answer choice A. Actually, B was incorrect for 0. I didn't realize until just now this was a 1. I thought this was a 0. I just glanced at it very quickly. So B we should have crossed out earlier because the probability that x equals 0 isn't even listed on here. But the correct answer is A. So the probability that x equals 1 is 0.42. We just add those two together. Okay, we're going to do a couple more of these using a very similar method. So suppose there's a 10% probability that any given person in the population is left-handed and a 90% probability that they're not left-handed. Say we randomly select two people and categorize them as left-handed or not. Here's a sample space showing the outcomes. So we're going to do the same basic idea for this. Not selected or not left-handed and left-handed. So the probability that they are left-handed is a 10% probability. The probability that they're not left-handed is a 90% probability. And so now we're going to say what these probabilities are. So the probability that neither of them are left-handed means the left-handed people equals 0, or x equals 0. And n and n, not left-handed, 90% chance, times not left-handed for the second person selected is a 90% chance, and that's 0.81. For the next one, probability that we have one left-handed person in this particular permutation, where n is the first person that's not left-handed, is a 90% chance. The second person is left-handed, that's a 10% chance. We're going to multiply that together. We get 0.09 for that particular permutation of one person being left-handed. Now we're going to choose the next way that we can write someone that's left-handed is the first person that we select is left-handed and the second person we select is not left-handed. So there's a 10% chance someone's left-handed and there's a 90% chance they're not left-handed, and we get 0.09 for that. And the probability that both people selected are left-handed, 10% chance they're left-handed, the first person, and 10% chance the second person's left-handed, and that gives us a 1% chance. So P, probability that x equals 0, is 0.81. That's our first section there. And it looks like C is the only one that has 0.81. A and B is not correct. But then if we didn't have that process of elimination, we could see now that the probability that x equals 1 is 0.09 plus 0.09, which is equal to 0.18, or an 18% probability. And we can see that's true on this table here for answer choice C on this part of the table. And 0.01 is the probability that x equals 2. Okay, we're going to try just one more of these. And the reason being, the answer choices are showing us a graph this time. It's the same basic idea, but we're looking at the answer choices graphically instead of with a table. Jillian plays darts professionally. Suppose she has a 20% probability of hitting the bullseye when she aims for it in a given throw. She's going to attempt 2 throws at the bullseye, and we can categorize each throw as hitting the bullseye B or not hitting the bullseye N. Here's the sample space showing the outcome. So same basic idea, the probability of getting a bullseye. Write that over here. Probability of getting a bullseye is, it says 20%, 0.20. And the probability of not getting a bullseye is an 80% then, 80% chance, because our probabilities have to add up to 100. Okay, so we've got first throw, second throw. We've got a table of these. So we're going to do the same thing we've been doing. I'm just going to write this shorthand now. Not making bullseye, two ends is 0.8 times 0.8. And that's 0.64. Not making a bullseye, making a bullseye, 0.8 times 0.2. And we're saying we're multiplying because it's saying that both of these things are happening, the probability of the first throw and the second throw. So if you're kind of wondering why we're multiplying, that's why we're doing multiplication for these. 0.16 bullseye, probability getting a bullseye is 0.2, not getting a bullseye is 0.8, that's 0.16. And finally getting two bullseyes, getting one bullseye the first throw and another bullseye the second throw, multiplying 0.2 times 0.2 gives us 0.04. Okay, so it looks like we have, again, this situation where we have two different ways that we can get one bullseye. And so we're going to add those together, and this is the probability that the number of bullseyes equals 1. And we're adding those together. 0.16 plus 0.16 gives us 0.32 for the probability x equals 1. This one's probability x equals 0, no bullseyes, 0.64. And 0.04 is probability that x equals 2 bullseyes. So now we're going to look at our graph and match the graph to this. So the probability that x equals 0 is 0.64, and that looks like C is the only one there that has where x is 0.64. The rest of these don't line up. And we can check for one bullseye, we got 0.32, make sure this is about 0.32. It looks like it is. And then where x is equal to 2, looks like 0.04. Yeah, that checks out. Okay. Actually, we're going to do one more of these even, because this next one is it's the same idea, but it's a lot tougher, I thought, because we don't have a complete table of yes and no this time, and we have to make the table ourselves. So I thought this was definitely a challenge problem. At basketball tryouts, Jeremiah will shoot a 1-point shot, a 2-point shot, and a 3-point shot, one after the other. So he's gonna shoot 3 different times, and the 1-point shot is obviously going to be closer to the basket. 2-point shots, a regular shot, and a 3-point shots from the 3-point line. So it looks like his probability of making these shots decreases as they get higher in points. So this is the probability of yes making the shot. And it says which graph represents the theoretical probability distribution of his total points. We don't have a complete table for this. So let's fill that out. And I'm going to write a new column for no, he didn't make the shot. So this is going to be, we'll leave it in the same percentages instead of decimals. This is 20% chance that he doesn't get the 1-point shot, 50% chance he doesn't get the 2-point shot, and a 70% chance that he doesn't get the 3-point shot. Okay, so we have a lot of different situations that could occur for this. So for the 1-point shot, you know what? I made a table for this just to save us some time on the lesson. So I'm going to put the table on here and explain what the table means. So if we're looking at if he gets no points, let's take a look at our first row on our table here. If he gets no points at all, here's what's happening. Um, he has a 20% chance of not getting the 1 point shot. That's here. He has of a 50% chance of not getting the 2 point shot and of not getting the 3 point shot, he has a 70% chance. Now he's taking 3 shots. He's taking 1 shot and 2 shots and the third shot. First shot is the 1 point shot. Second shot is the 2 point shot, and the third shot is the 3 point shot. So because he's taking 1 and 2 and 3, we're multiplying the probabilities. So we're multiplying 20% times 50% times 70% to give us a 0.07 probability of not making any of these shots. If he doesn't make any of these shots, he gets 0 points. So that's what our first column represents. So now the rest of this table is the different combinations that could happen. So the next part of the table is the next combination that could happen. What if he just made 1 point? Well, if he just made 1 point, then he gets the 1 point shot. Yes, he got the 1 point shot. And that probability that he got that 1 point shot was an 80% probability. And if he only got 1 point, that means that he would get the 1 point shot and not get the second shot and not get the third shot. So now we're going to multiply the probabilities of not getting the second point shot, which is 50%, not getting the 3 point shot, which is 70%. And so now we have our equation. 80% times 50% times 70% gives us 0.28. Okay, we're going to continue down this table for if he got 2 points, if he got 3 points, 4 points, 5 points, and 6 points. Now, we might not have to do this for all of these because they're multiple choice. So far we have 0 points is 0.7, 0.07. 1 point is 0.028. Let's see if we can find our answer just from that. 0.07 for 1 point. That looks like it could be A or C. So we can cross out B just from finding that one combination of 0 total points. Now we had 0.28 for 1 point. So let's see if 0.28 is on 1 point. Looks like for 1 point, this is less than 0.25 for C, and we had for 1 point is 0.28 for A. So A is the correct answer. Now that's just process of elimination with the graphs. I do want to emphasize though, for the 3 points, zoom out over here so we can still see our percentages. For the 3 points, there's 2 different ways for him to get 3 points. And I think that's like the most important part of this. It's probably the most important part of this problem is there's 2 ways to get 3 points. You could get just the 3 point shot, or you could miss the 3 point shot and get the 1 point shot and the 2 point shot to get 3 points. So again, the first possible arrangement of 3 point shots is not the first shot, not the second shot, yes, the third shot. And again, we're just using our table here, plugging in the probabilities, multiplying, and then we're getting an output. And so if we want to know the probability of getting 3 points, we would add together, just like we did in the last few problems, add these together to get 0.31 for our probability of getting 3 points. Now let's check to make sure that that's on A. 0.31 looks like it is. Looks like it goes to 0.31 there. Okay. All right, so this is your responsibility to make the table. I just made the table here so that way it was a little more clear and you can see all the data at once. So, quick review, I made the no column here to make sure our probabilities add up to 100. And so now we have happened or didn't happen, yes or no. And then we make our table for each of the scenarios. Now, there could have been instances where there were, here we had, there was two threes, but there can be times where we have two of other numbers or three of other numbers. So we have to add together all of those probabilities to find the total. Okay, the last section is on empirical probabilities, and this part's a little bit easier. I think it's a bit more intuitive to think about empirical probabilities. So, theoretical probability, what we just calculated were the probabilities of different outcomes based on what we know should happen. So now we're going to look at empirical probability distributions, and that's just based on data that's collected from an actual experiment, observation, or simulation. So instead of calculating what should happen, we look at what actually happened, and then we use those results to estimate the probabilities. So empirical probability is literally just the calculation for probability, the frequency of an outcome divided by the total number of trials. And I just put theoretical and empirical here for you. Theoretical is what should happen. Empirical is what actually happened, what data was actually collected. Okay, we're going to do just a couple of these because I think they're fairly straightforward. First example says Rosie is designing a board game where players roll two six-sided dice and subtract the numbers showing on the faces. The game only looks at non-negative differences. For example, if a player rolls a 4 and a 6, the difference is 2. Rosie simulated the differences of 1,000 rolls. Here are the results. And we have the difference of the two dice being rolled is 0, 1, 2, 3, 4, or 5. And it says, based on the results, which graph represents an approximate probability distribution of the difference on a random roll. Okay, so this is empirical probability. Rosie, she actually did this and collected all this data. So we're going to look at for the probability that x equals 0, where the difference in the two dice is 0. That is, we got 158 for our frequency. And she did this 1,000 times. So 158 divided by 1,000. And then we would change that to a decimal. So 158 divided by 1,000 is equal to 0.158. Okay, and the probability that x equals 1 is equal to 282. You can see that on our table there, over 1,000. And that is equal to 0.282. Okay, so now we're going to look at our table and just match them to the table. So I'm not going to do this for 2, 3, 4, and 5. We're just going to start with these two and see if we can find a match here. So the probability that x equals 0, we get 0.158. So let's see if we find any that is close to 0.15. Looks like B is a little less than 0.15. So not B. A looks like it is so far. Kind of skipped over because it looked like it already. And then C 0.158. It looks like that's less than 0.1, so we're going to cross out C. So it looks like A is correct so far, but let's just check one more data point here. 0.282 for x equals 1. 0.282. That looks like A to me. For B, for x equals 1, it's more than 0.3. That's not right. And then for x equals 1, it's not even at 0.2 for C. So we can just stop by doing these two data points here. and just match the graph. So again, very straightforward. We're not really adding two different instances of any combinations of things. We have actual data, and we're using that actual data to find the answer on the graph. Okay, we're going to look at one more with actual empirical data, um, except this time we have to find some missing values. It says, do not round your answers. So in this situation, it says Samantha is designing a video game where players get 3 free revives or extra lives per level. She wanted to test how many revives players might use on a new level. Samantha recruited 50 players to play the level, and she recorded how many revives each player used. And we have a table here, and it wants us to fill in the blanks. So it says revives used 0. There were 6 of them that were used. And then it looks like said we had 50 people total. So 6 out of 50 should be 0.12, and it is. Okay, so that checks out. Her column there checks out. So let's see if we can kind of write some more totals here. It might help us. So if we write this as our total column, we know that the frequency should equal, we had 50 people playing. So the frequency is 50. And we also know that our probability has to add to 1.0 or 100%. So we're just finding the totals for each row here. So now we can find the missing numbers here for this missing number. So 6 plus 22 plus 8 is 36. 50 minus 36 gives us 14 left over. So 14 is going to go in that box there. Same thing for this. We're going to use the total. We're going to add together these three values and then subtract from the total to find the missing value. So 0.12 plus 0.44 plus 0.16. 44 plus 0.16 gives us 0.68. Make sure I did that right. Nope. 0.12 plus 0.44. I did plus 0.4 plus 0.16 is equal to 0.72. Okay, and so we're going to do 1.0 minus 0.72 to give us 0.28. And I think this is fairly intuitive. This is probably things you've done in math before where you have to find the missing value from the table. All right, and I just wrote a quick summary here for you. So again, probability distributions, they show us all the possible values of a random variable X and the probability of each value. So all the probabilities have to add to 1 or 100%. The theoretical probability shows us what we would expect to happen. So if multiple outcomes produce the same value of X, then we would add their probabilities together. So that was those examples where the last one we had the basketball example where there was more than one way to get 3 points and we add the probabilities together. And then finally, empirical probability distributions, they show us what actually happened in an experiment, in a simulation, or in real collected data. And then we can estimate probabilities that way. Okay, so that is everything on probability distributions.